Imagine a world where artificial intelligence doesn't just predict the next word in a sentence, but understands the structure of thought itself. Where models don't just memorize patterns, but learn to reason, to plan, to simulate causal chains like a human mind. That's not science fiction. It's the frontier of modern AI, and it's being driven by a radical shift in how we train large language models. For years, we've trained models using a simple but powerful idea: predict the next token. Given a sequence of words, the model learns to guess what comes next. This is called autoregressive language modeling. It's incredibly effective, powering everything from chatbots to code generators. But it has a fundamental limitation. It's reactive, not proactive. The model only learns from the past, never from the future. What if, instead of just predicting what comes next, we taught models to simulate what could come next? Not just one path, but many. Not just a single outcome, but a branching tree of possibilities. That's the core idea behind planning in large language models, and it's transforming how AI thinks. Let's go deeper. At the heart of this new paradigm is a concept called tree of thought, TT, reasoning. Unlike traditional autoregressive generation, which produces one token at a time in a linear stream, TT treats the reasoning process like a search through a decision tree. Each node in the tree represents a potential thought or step in reasoning. From each node, the model explores multiple possible next thoughts, evaluating them, pruning poor paths, and selecting the most promising ones. This is not just a fancy way of saying think harder, it's a structural shift. The model is no longer just predicting the next word, it's evaluating entire sequences of reasoning. It's asking, what if I consider this idea? What would happen if I took this step? Is this leading toward a valid conclusion? To make this work, we need two key components: search and evaluation. First, search. How do we explore the space of possible thoughts? Instead of following a single path, the model generates multiple candidate thoughts at each step. It might consider 3, 5, even 10 different directions. Then it uses a planning policy, a learned or rule-based mechanism, to decide which branches to expand further. But here's the real breakthrough: evaluation. The model doesn't just generate thoughts, it scores them. It asks, how plausible is this idea? How close is it to the goal? Does it contradict earlier assumptions? This evaluation is often done using a separate, lightweight model, or even a prompt-based system that simulates a critic. For example, imagine the task: solve this math word problem. A train leaves station A at 60 mph. Another train leaves station B, 100 miles away at 40 mph. When will they meet? A standard LLM might just start writing an equation and hope it's correct. But a TT model would explore multiple paths. Path 1, set up equations for distance equals rate times time. Path 2, try drawing a timeline. Path 3, consider relative speed. At each step, it evaluates which path is most likely to lead to a solution. It might discard the timeline idea if it's too vague, double down on the equations, and then test the solution by plugging in values. This isn't just better guessing, it's structured reasoning. And it's why TT has shown dramatic improvements on complex tasks like math problem solving, logical reasoning, and even strategic planning games like chess or Go. But TT isn't the only approach. There's also chain of thought, COT prompting, where we guide models to think out loud by asking them to generate intermediate reasoning steps before answering. COT works well, but it's still limited to a single path. It's like writing a single draft of an essay. TT, by contrast, is like writing multiple drafts, comparing them and choosing the best one. And then there's self-consistency, a technique that combines multiple COT traces and selects the most frequent answer. It's a form of ensemble reasoning, but it still lacks the depth of true search. Now here's where things get even more advanced: reactive planning. In real-world scenarios, the world changes. A model can't just pre-plan and hope for the best. It needs to adapt. Enter online planning, where the model continuously updates its plan as new information arrives. Think of a self-driving car navigating a city. It doesn't just compute a route and stick to it. It monitors traffic, road closures, pedestrian movements, and recalculates in real time. The model uses feedback loops to adjust its reasoning, making it robust to uncertainty. This is where reinforcement learning meets language models. Some systems train models not just to generate text, but to maximize a reward signal, like solving a puzzle faster or making fewer errors. The model learns to explore, evaluate, and revise its plans to optimize performance. This is how models like DeepMind's AlphaGeometry or Google's Minerva achieve near-human reasoning on Olympiad-level math. But here's the critical insight: planning isn't just about better answers, it's about better process. When a model plans, it reveals its internal logic. You can see how it arrived at a conclusion. You can audit the reasoning. This makes the model more transparent, more trustworthy, and more useful in high-stakes domains like medicine, law, or engineering. And this isn't just theory. We're already seeing practical applications. In code generation, models now plan entire functions before writing a single line. They sketch out variable names, data flow, error handling, then generate code that's more structured, more correct, and easier to debug. In scientific discovery, models are using planning to generate hypotheses, design experiments, and interpret results. They don't just predict molecular stability, they reason through the physical principles behind it. So what's next? The future of AI reasoning lies in hybrid architectures, where language models are coupled with symbolic reasoning engines, neural planners, and external memory systems. Think of a model that uses its language understanding to generate ideas, a symbolic engine to verify logic, and a neural planner to explore options. We're moving towards systems that don't just respond to questions, but think about them. And that's the real revolution, not just bigger models, but smarter processes. Not just more data, but better reasoning. Because at the end of the day, intelligence isn't just about knowing more, it's about thinking more clearly. So the next time you ask an AI a complex question, remember, it's not just giving you an answer. It's working through a maze of possibilities, pruning dead ends, and choosing the best path forward. And that, right there, is the future of artificial intelligence. The most powerful tool we have isn't the model. It's the process. And the process is planning,